Okay, so we'll just get going. So first speaker we have is Dr. Christopher Scholz from Syracuse University, who'll be talking about bathymetric mapping of the lake. Okay, looks like we're in business.
Thanks, Steve.
Yeah.
Thanks, Steve. Thanks, Frank and Charlie, for organizing this really nice event today. It's a pleasure to present to you today some of the work that we've been carrying out since last spring, investigating the lake bed of Skaneateles Lake. Just a quick shout out to the science team that's really been doing the heavy lifting here. Doug Woods, our lead analyst, who's been directing the field program and leading the data processing, as well as Nick Brennan, who's also here, a doctoral student, who's going to be doing the lion's share of the analytical work moving forward. Right. So why bother studying the lake bed? Right. It's we don't see it very easily from the shoreline. We see a little bit, but we've got all this information about the watershed itself. We've got all these fantastic GIS layers where we've characterized aspects of the catchment, but we don't know that very much about what's going on underneath that water column. But it is the sink or the sump for all the discharge coming off the land surface, right? So that's where all of our pollutants are ending up. So we need to have some sense of what's going on down there. And knowing the first order, knowing the shape of the lake bed is really important. It can provide information for man-made infrastructure. It's important for characterizing the water budget and undertaking hydrodynamic analyses of the system. It can help calibrate some of our drone and satellite imagery. We get information on shipwrecks. It can improve navigation. As a geologist, it's important to study the lake bed because we can get a sense of the bottom type, the different sediment grain textures, the type of vegetation that extends across the bottom gives us information about bottom habitat for both native or introduced species. Our particular project is keen to understand the extent of nutrient-rich sediment reservoirs. We know that from previous work, and Charlie and Mike Kelly are going to talk about this work shortly, we know that phosphorus abundance in the sediment increases dramatically as you get into slightly deeper water. As you get into water depths of 15, 20, 25 meters, there's a fourfold increase in the abundance of phosphorus in the sediment. So if there are mechanisms, like Mike will describe shortly, for bringing those nutrient-rich sediments into the upper waters, we have a forcing mechanism for potentially producing very significant harmful algal blooms. Right, so the key questions for our study, our science study, are where are these high nutrient bottom sediments exactly? And to determine that, we need to know the shape of the lake bed, and we need to know the extent of the so-called wash zone or erosion zone that is present in the northern end of Skaneateles Lake. It's actually present at the northern ends of almost all of the Finger Lakes, in our opinion. And this erosion is not a consequence of normal wave action, but it's a consequence of breaking internal waves that we'll hear about further. But there's other things we can learn from mapping the bathymetry of the lake bed, where we pose the question, are there deep water pockmark areas in Skaneateles Lake similar to what have been described and observed in Seneca Lake? Is there any evidence for underwater landslides in the system? I mean, this is actually a non-trivial risk of near-field tsunamis in enclosed lake basins. These kinds of events have been described in many lakes around the world. And for geologists, we're interested to learn if there are features from the glacial era or perhaps the earliest phases of Skaneateles Lake. So just a quick reminder here, we've got Skaneateles Valley was 20,000 years ago, 18,000 years ago, was completely covered by ice. Our whole region, of course, was completely covered by a continental ice sheet. Upwards of 2 miles thick ice covered our area and completely transformed our landscape. Over time, over a period of perhaps 5,000 years or more, that ice front retreated from Long Island and northern New Jersey and moved northward, melted northward into the Finger Lake valleys. And for at least several hundred years, perhaps even a couple of thousand years, there was a massive wall of ice right at the northern end, or at the ends of all the Finger Lakes. And we call this the proglacial lake phase of this system. And the landscape was completely altered, of course. There was a tremendous amount of sediment that washed into these valleys during that phase of the lake. And then perhaps beginning around 11,000 years ago, the ice moved out of the catchment completely, and we had this gradual transformation to what we know as modern Skaneateles Lake, this beautiful oligotrophic system. All right, so that's kind of the backstory for a lot of the imaging that we're carrying out here. So in 2025, we carried out this bathymetry and backscatter survey of the lake using a multi-beam echo sounder, and this technique uses acoustic energy to scan the lake bed in broad swaths. We actually can image the lake bed over a distance, a given swath that's about 3 times the water depth over which the boat is surveying in. And over on the right side of the screen, you can see the survey tracks from our project in July and August. We spent about almost 6 weeks out on the SLA research boat, the Bob, acquiring these data. And you'll notice that the survey tracks are far more concentrated in shallow waters, right? Because it takes much longer to cover that terrain, whereas the deeper waters we can cover relatively quickly. The swaths are that much wider. Right, so we collected 3 main data sets or sample sets over this past field season, and they yielded the lake bed bathymetry, right? We know the shape of the lake bed now. We've also collected this backscatter information or reflectance information, which gives us information on bottom type. And we also collected a series of lake bed samples in slightly deeper water than had been available previously. And Charlie Driscoll is going to speak about some of those analyses in his talk this afternoon. So we've completed the bathymetric data analysis and the sample collection. The backscatter processing is now underway to investigate the type of bottom that we find across the area, and we're also starting off the geochemical analyses on the sediment samples. So I'll mention that very briefly. Right, so there was previous bathymetric information from the lake, but it was relatively crude data. Actually, our team collected this almost 25 years ago, and that data was acquired with an uncalibrated seismic profiler. It was not a hydrographic survey instrument. It was what we refer to as sort of single beam sampling with relatively widely spaced survey lines, required interpolation between those lines, and it didn't include any backscatter information. Whereas our current survey uses this calibrated hydrographic survey instrument. As we're collecting the data, we're also making casts in the water column, measuring sound speed and temperature, so we can make for corrections of sound energy refraction in the water column. And so this multi-beam swath bathymetry tool sends out more than 1,000 beams to the sides of the vessel, and it gives us complete overlapping coverage. And we can produce a digital terrain model of the bottom. And nominally, right now, we have a data set of the entire lake of a 1 meter grid, and in some areas we have even finer than that. And we're in the process, as I mentioned, we're in the process of starting the processing of the backscatter bottom type analysis here. So just a couple examples that I'd like to show you. This is a bathymetric DTM of the area right around the Syracuse, city of Syracuse water intake. And don't worry, Rich, we filtered this out of the main data set. We're not going to share the location of this guy, but you can see quite clearly position of this. And it's quite informative. And the texture that you can see all around the water pipe itself is in fact real lake bed sediment texture or geology through there. So there's a lot of information available. So this map shows the entire data set that we acquired and processed, combined with LiDAR data, that is light imaging radar data from the state of New York. And we observed a maximum water depth of about 87 meters that is observed off of the Fall Brook area in the central southern part of the lake. And it's, you can see quite clearly in here you can see if I can make this guy work. You can see the very steep sides of the southern parts of the basin. Right through there, there's this gradual shoaling margin. I'm not sure this guy is really showing up. You can see that shoaling margin to the north end. That turns out to be very important in terms of nutrient loading. And also we have these shallow shelves at the very northernmost and southernmost parts of the lake. Those shelves weren't there prior to the installation of the dam in the early 1800s, right? Those were swamplands, basically. So that's a very significant change in the character of the lake, and that has implications for water column processes. And perhaps Charlie will touch on some of that later this afternoon. Just another example of some of the data, some of the observations from the bathymetry work. This is, on the left side, you can see a detail of the bathymetry off of Sevi's Marina there, and you can see a number of these significant distributary channels in the system. And if we look at the backscatter of this area, you can see the strong contrast in bottom type from within those channels to the inner channel areas. So the lighter colors are coarser grained sediments being delivered right off of that stream that's coming in right at Sevi's, right through there. So there's a lot of detail in some of these data. If we move up to the north, sort of the central part of the lake off of 5 Mile Point, we notice some very interesting textures in the bottom of the basin. And if we zoom in, we can see a series of these pockmark structures all through this area. If I zoom in a little further, you can see some of the details. These are about 100 meters wide or so. On the right side of the screen, we have a high-resolution seismic reflection profile. It's another acoustic image, not of the lake bed, but of a slice of the sub-bottom. And we can see the deep divot just adjacent to these big pockmarks right through here. These are similar, these features are similar to what are observed and widespread, actually, in the southern part of Seneca Lake. That information is just being published by the group at Middlebury College. We're not entirely sure about the origin of these structures. They're very likely related to processes of ice retreat and glaciation. Perhaps they're ice collapse structures. Has been suggested that they may be associated with groundwater discharge or even gas discharge. Some folks may have heard about the Seneca drums that are legendary in Seneca Lake that are postulated to be a consequence of methane gas eruptions from that system. So this warrants further research, especially if they may be associated with groundwater discharge or perhaps even saline water discharge from salt formations in the subsurface. So we see a number of really interesting features in the northern ends of the lake. We can just in the far north, we've got the drumlin that extends off of 1 Mile Point, off of the country club that's very prominent in the lake bed right through there. The wash zone, the erosion zone, is present all through this northern area. And as I mentioned, we're just starting the processing of the backscatter data, but we also see from our seismic reflection data that some of this lake bed is in fact underlain not by modern lake sediments, but some of those proglacial lake sediments that have been exposed due to these internal breaking waves. A number of other interesting features here. Shotwell Creek Delta is very prominent in this part of the basin. It's built out considerably across the lake bed here. But we also see some interesting features that are related to much earlier phases of sedimentation in the basin going back probably 13,000 years. We can make out very clearly a sinuous ridge, which we interpret to be a glacial esker. These are stream deposits that accumulated underneath the glacial ice sheet, right, when there was thick ice in the system. So we see this high sinuosity ridge extending for, 1.5 kilometers or more on the bottom of the lake. It's sticking up above the lake bed. Also a very prominent knob, which we interpret to be a came, another type of glacial till deposit in this particular system. And the sketch on the lower right is a conceptual model of these of the accumulation of these kinds of materials. Right. There's also some examples in different places of significant in-lake landslides. So we can see both off of Jenny Point and Staghorn Point several of these deposits here. And our hope is to return to this area with our seismic profiler and our sediment cores this coming summer and determine the age of these slides and look at them in a little more detail. As I said, it has been shown in other lake systems that in-lake slides can actually produce non-trivial wash-up as a consequence of nearshore tsunamis in these kinds of environments. So we want to investigate this a little bit more carefully. Another example of a in-lake slide just north of 5 Mile Point in this system. Right. So I mentioned that we also collected some sediment samples during our summer field campaign. The green triangles are data that we acquired several years ago, part of Mackenzie Brannon's doctoral thesis. And I think both Mike and Charlie are going to make mention of the data from those green triangles, and also this pink hexagon down here is the site where we've carried out a historical nutrient study, which is the focus of Charlie's presentation this afternoon. But the white squares are the samples across this erosion zone that we collected this summer. So we are just starting out some geochemical and sedimentological analyses of those samples to determine how enriched they are in phosphorus, how enriched they are in organic constituents. And we'll also characterize the texture of those sediments. So the plan here is to use these sample sets to calibrate our backscatter data to really map out precisely the extent of that nutrient-rich lake bed zone, that wash zone, if you will. Right, so just a summary of the main products from the study. We've completed essentially the main bathymetric mapping and processing work. We're going to be producing an atlas of lake bed bottom type and character, and also carrying out geochemical analyses of these lake bed sediments. And these results will be provided in the form of internal reports to SLA, and we'll continue to work at these outreach events, and we expect a couple of peer-reviewed publications to emerge from this work over the next several years. I did want to mention that we shared the initial data set with a local mapping company east of Nowhere, and they are famous for combining geographic information with artwork, and you can purchase a map of Skaneateles and the lake bed from them if you so wish. But we'll release the primary bathymetric data later this year. Initially, a 10-meter grid will be released and put into the state archives. And then as the peer-reviewed publications emerge, we'll release the high-resolution results of that grid. Right, so thank you very much. Stay tuned for further deliverables and outcomes from this work. We're really excited about it. And again, thanks to SLA, to the NAPPIs, and various institutions that have supported the work. Thanks.
So we have about 5 minutes for questions. If you have a question, I'd ask you to step to the microphone. So online, listeners can also hear that question. The microphone, feel free to hop on.
Thank you so much. Pretty exciting maps of the bottom of the lake. I think I asked this question earlier, but how much is the spatial resolution of the bathymetric map?
Right, so we've processed to 1 meter so far for the entire lake. So we have a 1 meter grid for the entire lake. Selected areas, we've produced some preliminary maps at 0.5 and 0.25 meters.
Then one other quick question. Where there are aquatic vegetation, how does this impact your sonar backscatter?
Oh, that's a great question. I mean, we can make some casual observations about where we have vegetation now. It definitely impacts reflectance of the data. We've not yet quantified those observations, so that's kind of work that's forthcoming. For sure, we'll be able to map out areas of significant vegetation in the shallow waters. Yeah.
Good morning, and thank you, Dr. Shaw, for a most interesting presentation. My question, do you think the rapidity of the glacial retreat presents any particular features in Skaneateles Lake and or the Finger Lakes generally? Thank you.
That's an interesting question. You know, we actually don't know how fast the ice moved out of the basin. It's been speculated that it's on the order of as short as just a few hundred years to retreat, you know, across the entire system. You know, it's a question I'd love to dive into a little deeper, but to really refine that is kind of a heavy lift, right? Because we need deep samples to really determine the timing of that full-on retreat. It's not surprising that it was relatively quick, but based upon the fact we're seeing these subglacial features in the basin, suggests that yeah, it retreated fast, and there was a proglacial lake there immediately. So we didn't erode those eskers or those cames, those other features in there. So you know, based upon what we've seen in the seismic reflection data from Skaneateles and other lakes, this remotely sensed acoustic sub-bottom profile information, you know, 500 years to maybe 1,500 years might be a reasonable estimate for the time of retreat there, but it's still kind of speculation.
Is there any photographic evidence of the nature of the swamps at the north and south ends of Skaneateles Lake? In other words, the nature of the way the land looked at the north end of Skaneateles Lake before the dam went in,
right?
And the south end.
Yeah, that's a great question. Well, we have our acoustic imagery, right? But there's no, you know, it's been speculated, or if you go into the historical literature, there's documentation of wetlands all across that area, right? It was swampland before the establishment of those dams in the early and mid 19th century. So it's completely altered, right? There's no more vegetation down there. We have a lot of hard ground, carbonate cemented sediment for the most part. So it'd be worth diving a little deeper, though, into the acoustic information to see if there's any relict information. There's a lot of interesting phenomena down there. I'll just show you one other image. This is backscatter information off of 1 Mile Point, off of the drumlins. We have all these weird donut-shaped features all across this area. And if anybody has any idea what have produced these, they're about 3 meters in diameter, right? And they're very distinctive. It almost looks like it was a mooring field or something at some point in the past. If anybody knows anything about the history of the lake and can share some insights, I'd be really delighted to hear about it. It's an area I'd like to go scuba diving on this coming season to actually see what's down there. So there's a lot of interesting stuff that we just don't know about, and we need to drill a little deeper into the data sets. Thanks very much.